We are going to Abisko to do the Kungsleden trek. And yeah, hopefully we won't get too wet or too burned in the sun.
If we look at this graph here, this is the present time, so around 2000. And look, we can go back to the year 1000, to the year 900. And actually, we have climate data that goes back 7,400 years for Abisko. How do we get that? Anybody have an idea how we get that? Tree rings. We can use tree rings to understand what was going on in the climate in the past. And what you can see is that there are different phases in our climate over the long term. And what we can see is that it was cold when the research station started, and it's warm today. The temperature in terms of a real difference is almost 1.6 degrees. And almost all of that has occurred since the late 1980s. So what's happened is that essentially, as we have put CO2 in the atmosphere from burning fossil fuels and doing other types of things to our climate system, the Arctic has taken a long time to really warm up. But now you can clearly see that we are entering a very warm phase. So here, we had the environmental conditions that allowed permafrost to exist, and we had alpine glaciers in the mountains. Today, the permafrost is thawing, and the glaciers are melting. Now, when I say Arctic, what do I mean by Arctic? Well, for the everyday person, the Arctic or the polar circle is just that region where you have at least one day of 24-hour daylight in the summer and one day of 24-hour darkness in the wintertime. But for scientists, we use different definitions of what it means to be the Arctic. The Arctic for us is what we call the cryosphere. It's where the mean annual temperature is below zero. So that doesn't mean that there aren't warm days and really cold days, but essentially if you averaged the temperature for the whole year, it would be below zero. What we can see in 1913, the only places that the mean annual temperature was above zero was right along the shore of the lake. But look by 2008, how dramatically that's changed. We have crossed that 0 degree threshold sometime between 1913 and 2008, and it's expanded, and it's still expanding today. But that 11 degree threshold has not really changed, and that's a summer measurement. So that means that most of the climate change that's occurring in the Arctic is not occurring in the summertime. It's occurring in the winter, spring, and the autumn. And that has profound implications that we'll talk about later. So even though we have an overall increase in the mean annual temperature, most of that is not driven by summer temperatures. But another thing that we can think about when we think about the climate up here is the ice on the lake. I mean, you can see right now the snow's melting quite quickly because we didn't have a lot of snow this winter time, but the lake is still frozen. I mean, you can still ski across the lake to the other side if you felt so inclined to do that. And so we've been actually looking at the date that the lake freezes up every year, and then the date that it starts breaking up every year. And you can see that the complete ice cover, which occurs in the winter, is becoming later and later, meaning the lake is freezing up later in the winter time. But then the thaw is becoming earlier, year after year. So that means that the period of the year where the lake is not frozen is longer. Now, why is that important? So imagine you have the Arctic. So this is the view of the north from the North Pole. Here's the North Pole. Okay? Now, if this landscape is all white, how does that differ than if that landscape is all dark? So let's just say this is dark and this is white. So this is snow and ice landscape. This is a dark landscape. It could be water or it could be brown soil, vegetation, rocks. When the sunlight comes down, so the solar radiation, hits a white surface. It reflects 85 to 90% of the energy back up. But when it hits a dark surface, only reflects about 10% of that energy. So what you can see is that as we affect our climate and warm our planet, and this ice starts to melt, a feedback starts happening, where you get less white surface, more dark surface, which means more heat storage, more warming, which means more loss of ice, more loss of snow, and so on and so forth. Snow cover. So not ice now, but we're talking about snow. If we look at this as from a published paper, where we looked at the mean monthly temperature average, not temperature, snow depth average, from 1950 to 70, this is the middle of the winter, February, March, okay? By 1986-2000, look at that, we've had an increase in snow cover. Now why is that? Why would we get more snow if we have global warming? Do you have an idea why that might be? Essentially, as the atmosphere warms, every degree of warming in the atmosphere increases the amount of moisture it holds by about 7%. So the Arctic is still cold in the wintertime. It's just warmer. So that means that we get more snow. Now we haven't, I don't have a good plot, and I intended to create one. There was a paper that came out last year that actually looked at the data since 2000 to recently, and you know what? It hasn't increased. The snow depth hasn't increased. And the reason being is because now it's getting so warm, we're getting repeated rainfall events in the wintertime, which reduces the snowpack. The downside is that this landscape used to have a lot of permafrost in these mire areas. And I'll tell you a little bit more about permafrost. So we get an increase in snow. It means the ground doesn't freeze as hard, which means that that permafrost will thaw in the summertime. So in this study here in Abisko, this is the first year of the study, the 4th, the 6th, the 7th, and the 8th. The blue, those are the control plots where we've done nothing. These are 3 different versions of experimental manipulations where we use the open-top chambers. And what's important to see here is the response variable, meaning how does the environment respond? We see an increase in this ecosystem respiration, meaning that we have more CO2 being released because we've increased the amount of biological productivity. Now, why is that important? Well, because instead of that carbon being underground, now it's being breathed out by the bacteria and the soil organisms into our atmosphere. And so this is a feedback. So you think about climate change. Everybody here probably is in agreement that we need to do something about burning fossil fuels, right? So what happens if we turn off all fossil fuel use tomorrow? Does the climate change? Does the climate start to all of a sudden the temperature starts to go back to normal? What do you think? The CO2 has a lifetime in the air. And we've moved so much carbon from underground into the atmosphere and into the oceans that the reality is that based on model projections, that it'll take about 400,000 years for our climate system to resume kind of its natural cycles. So that's today. That's not based on what happens if we kind of actually get our act together in 30 years or 50 years or 100 years, which is kind of where we're heading, right? That's based on today. So the problem is not only that if you turn off the taps of fossil fuels that the CO2 stays there, but you get these feedbacks from the ecosystems. Because it's so much warmer, you get this increase in biological productivity, and you get the increase in the ecosystem respiration, which means that even though we're not putting more CO2 up from factories and cars and things like that, the CO2 levels just keep increasing and increasing and increasing for some very long period of time because we've warmed the planet so much.